right, let's get started. So first of all, thank you for coming to this special session on immersive media organized by the 5G Reference Tools team. We've prepared today 5 slots with presentations. Actually, our intention initially was to provide some updates on the 5G Reference Tools for XR supporting MPEG-I in description and also the V3C immersive platform. So we'll have Nils from Motionspell and Patrick from InterDigital covering these 2 topics. But actually we thought, well, we've seen other work related to 5G Mark that is happening somewhere else. And one of these pieces of work comes from Lausanne University of Applied Sciences and Arts. And actually, Aljosa was presenting at IBC this paper on efficient streaming of volumetric video with GLTF, which we thought was closely related to the 2 topics above, and we wanted to hear from him about the work of his team. We are also taking advantage of having Thomas and Imed here to, let's say, delve a bit into MPEG Avatar and the work that happened in release 19 in terms of a study item in 3GPP. And the idea here is to see if there is a chance to detect work for the 5G reference tools. And finally, we have also invited Mario from I2CAT, as he is leading some European projects that are dealing with XR, with teleportation. There's also a link to volumetric video, or at least to the reconstruction of volumes, for instance, for conferencing and so on, and also the use of network APIs. In this sense, I think it relates to Camara, in order to discover capabilities of the network, for instance, for edge computing, that can be applied to these scenarios. So let's start with Nils. So Nils, if you are ready, the floor is yours. Please go ahead.
Just quickly to introduce what the project is about. The project takes scene description document, which is in a document in GLTF format, and implements MPEG specific extensions. And the specification that describes these MPEG extensions also provides a description of a media access function API, which is referred to as MAF API here. This API allows decoupling of a presentation engine, so typically a game engine or rendering engine, from the media pipeline that are fetching and exposing buffers to that rendering engine. So the GLTF document provides a description of the media through extensions, and provide extensions to buffers and accessors that allow describing the media and exposing it to the presentation engine. So this can be used, for instance, for video textures, for special audio, which have been specified also in the scene description format. But the buffer format is really much more flexible than that, and it allows to pass geometry buffers or arbitrary data. One thing that maybe is not emphasized here, and I should develop further in the slides, is that the media access function API allows also not only fetching, but also providing feedback to the media pipeline from the rendering engine, for instance, by passing the current viewports, so that the media pipeline maybe allows some optimization depending on the viewport. The scene description framework also provides several extensions to nodes and other GLTF elements to provide interactivity and extended reality support. So interactivity that is implemented as an action trigger an action trigger interactivity scheme where some triggers are defined in the format, and in result of those triggers and the combination of those triggers, several actions can be taken. For instance, trigger would be if two nodes in a scene get close to each other, then it will trigger some action. Another trigger available would be if an object becomes available in the viewport. And there are several triggers that are defined in the scene description format. I recommend that you check out the MPEG group scene description repository, where the JSON schemas for these extensions are all provided. So the XR Player project is a Unity project that is composed of several components, several packages, and it also comes with some test content that can be used to test the player, and that provides some examples of the scene description format. And there is also a very basic Blender exporter, which is currently only supporting video texture and special audio nodes. But we intend to provide more tools to be able to provide content and to simplify the production of test content for the extensions that are currently supported by the player. These repositories, I will go through it very quickly. The XR Unity player is a Unity project to load and render MPEG-I scene description document. It's basically the entry point to everything else here. The media pipeline factory and plugins implement the media access functions that I mentioned at the beginning. It is a C++ implementation that comes with a factory and a plugin system, so that you can implement new plugins and extend it. So right now, this has been initially developed with a plugin that implements a simple libav decoder, but I intend to provide more documentation and tutorials to actually develop new plugins. You should, if you are interested in this area, you should keep an eye on the repository and the project. The MPEG-I scene description GLTF extension is implemented through a fork of the GLTF fast project, and the other repositories are like I said, the MPEG-I scene description assets and the initial Blender extension to generate such assets. So in terms of features, currently the XR player is released as version 1.00. We tagged version 1.00 as the first Android version of the player. It supports MPEG Encore and MPEG interactivity as contributions as contributed by InterDigital. MPEG Encore allows anchoring nodes to 3D objects. So you will think about XR, obviously anchoring 3D objects in the real world, but this can really be more than that. It can be anchoring to the viewer itself. It can be also anchoring to a controller. There are actually several options. Currently, only a subset of these options is thoroughly tested in the player, and we intend to provide more examples for the ones that are not as thoroughly tested. The MPEG interactivity extensions define interactivity behaviors on the scene and the nodes themselves. This is available on Windows and Android already. The media pipelines in the version 1 of the player are only supported on Windows. They enable video texture and spatial audio. The current development of the player is v1.1.0. I haven't tagged yet this version, but this is getting really close on polishing everything. And this version will support media pipelines on Android so that we can combine these savable extensions in our demos, the MPEG Encore, MPEG interactivity, and media pipelines. And also it will provide more documentation to implement custom media pipelines. So this is about it on the XR player for me today. If you have any question, I'm happy to provide further details.
Perfect. Thank you, Nils. Sorry, Jordi.
No.
I figured since I'm back.
We don't have questions in the chat, but I wanted to introduce you actually, Daniel. So Daniel and Nils are let's say, taking care of the coordination of the reference tools. Nils in particular on the immersive media projects, and Daniel is overseeing the entire reference tools group. So Daniel, it would be nice if you would point us now to, let's say, where to access the projects, how to contribute, as the community is also open. So some details on this would be nice. And of course, questions for Nils on the chat or online, also welcome.
Okay, so I joined a bit late, so I'm not sure if Nils mentioned this before, but everything we do is on GitHub, and I'm going to put the link in the chat. So you can contribute to the tools, even if you're not a 5G member. You need to sign our CLA, and that's it. And basically everything that Nils showed today, and also that we do next to XR and V3C, we will come to this in a bit, is available on GitHub, as I said. So 5G media streaming, 5G broadcast, and the other activities, everything can be found on GitHub. If you have any questions, you can always reach out to me. We have a landing page at 5gmec.com. There's a special section on the reference tools. And yeah, as I said, so contact me if you have any questions, contact Jordi. Otherwise, find us on GitHub, and you will also find a dedicated web page focusing on tutorials for all the different projects that we have. What do you need to do in order to reproduce what Nils showed today, or any of the other implementations that we have? Everything is available as a tutorial to get you started. And we are also working on Docker integration right now, so to make this as easy as possible for you guys. Yeah, so much from my side. And then let's check. Do we have any questions for Nils?
No question. So I will stop sharing and let you take over.
There's a hand. I think it's Jordi.
Yes, so I have a question for Nils actually. So Nils, just to clarify, so basically in the current APK that let's say we can install in our phones, for instance, the tools that are currently available are MPEG Anchor, interactivity, and you are currently working on the media pipeline support for Android as well, but that's not yet released. Is that right?
Yeah, so I actually just updated today the repository for the media pipelines to support Android building, and provided helper scripts to install this in the Unity project. And I need to update the documentation on the Unity project side, and then we will be ready to tag initial version, like a beta version for Android support of media pipelines. And then I will be working on providing more tools and test assets for this feature. So yeah, it will be available in the coming days, this v1.1.0. The media pipelines are working on Windows currently.
Perfect, Nils. Time to test then. I see more questions, Daniel. Let's go.
Yes, one question from Imed, and then we also have one in the chat. Go ahead, Imed.
Yeah, thank you. Thanks, Nils. This is great progress, of course. So I was wondering, I have two questions actually. So on the pipeline on Android, are we using media codec directly, or is it still a port of libav? That's the first question. Second is, does that mean that we can now probably run natively on Oculus, for instance? Have you tried that, or is it like on smartphones with AR core? Is that what's the target is?
So to answer your first question, we are not using media codec directly. We are using media codec through libav at this point. But I would like to stress that like improving the documentation on the system to the plugin system for the pipelines will be helpful to implement media codec also. But no, it's not dealing with the media codec API directly at this point. And yes, that means that it would be possible to run on the Oculus. I have yet to do more tests in this field. What I'm not sure exactly about is the status of MPEG Encore on the Oculus itself and MPEG interactivity. I will have to check that. But for media, I expect this to work.
Okay, great. Thank you.
Thanks, Nils. Thanks, Imed. Then one more question in the chat before we move to the next presentation. So Marius is asking, there's a roadmap, or is there a roadmap on what other tools from MPEG will be integrated in the new feature?
So the roadmap right now is the v1.1.0. We are discussing the possibility to integrate avatars in the framework and other tools from MPEG. So maybe we can discuss this further, but there is a potential for integration with V3C if there is traction. But V3C right now is a separate project altogether. Because the media pipeline, the math API also the scene description standard also specifies all V3C could be integrated in the scene description through media pipelines.
Okay, perfect. Thanks, Nils. Let's move on. Thank you for sharing. Next, we have Bart and also Bart Kroon from Philips, Thierry Filoche from InterDigital, and also Patrick Fontaine from InterDigital. And they are going to talk about updates on the 5G Make reference tools, V3C, Immersive platform, including support for MPEG-I V3C volumetric video. Bart, you guys are ready, or Patrick, you're going to share?
Yes, so Patrick speaking. Actually, I will be presenting.
All right, go ahead.
So, okay, you can see my screen.
All good, we see a screen.
Okay, so I'll give a quick overview of the V3C immersive platform. So the implementation that is now available in 5G reference tools. And just before, I will have 2 or 3 slides on recap on the standards that we are implementing. So the immersive video standards in MPEG are under the umbrella of V3C, which stands for Visual Volumetric Video-Based Coding. And for the acronym there, VPCC is the codec that is that uses point cloud as an input and follow the V3C format. MIV is for multi-view plus def and multiplane image content. So these are the 2 codecs that are available in the platform. There is a third codec for mesh coding being specified. And also for when we talk about immersive, it is important to have also different aspects, and now there is a haptic that covers more immersiveness, and this haptic standards is being specified now, and it will be integrated in the platform, so I wanted to mention here. And then there are the two specifications for carriage of the data, V3C and haptics, which can enable MPEG transmission. And lastly, the same description that was previously presented by Nils that enables composing the scene compositing, and that can include media components such as also volumetric video and haptics. So actually, these standards in MPEG are at a different stage. The V3C and point cloud VPCC are published versions. And MPEG-MIV, there is a first version, and the second version is in final draft. And the carriage of V3 data is also published. So these are quite finalized specifications. It is the same for haptics, which is just recently published. Just to mention also that in 3GPP, there is a feasibility study, a technical report that is being written for evaluation and characterization of VM2D video format and codecs, and covers from 3D, stereoscopic, and volumetric video. So to give a visual representation of what is a volumetric video on the left here, it's a point cloud, a dynamic point cloud, which in fact are points in the 3D space that are evolving in time. So which enables 6 degrees of freedom for the end user directly from the end device. And on the right, it's an example of a multi-view plus depth, which take as an input multiple views and also the depth information of each views to create a 3D representation of the scene. And it enables also 6 degrees of freedom, and you can feel the sensation of depth and parallax. So that's it for the quick introduction, and I will go to the V3C Immersive platform in 5G MAG. So this has been introduced in 5G MAG around June last year, and this is an overview of the pipeline. So we start from the top left with the content that are pre-recorded, so they can be captured in studios with multiple camera setups. So with the different format, point cloud or multiple plus depth. Then these content are encoded with, so today we are using MPEG reference softwares for VPCC MIV. And the output is then a V3C bitstream. So this output can be directly used in the platform for local playback on the device, or it can go through Dash Packager, which is where we added the support of V3C to encapsulate and segment the content so that it can be pushed onto a Dash server for remote access from the Immersive platform. So actually, what is today on the 5G MAG reference tool is the figure from on the bottom, the Immersive Video Decoder platform. It is mainly composed of two main parts. So the host application, which is a Unity application, in fact, and that can be run on Windows or Android end devices. So this application is to render the scene and to request the actual view that is being that the end user want to see. And it relies on the native decoder plugin, which is written in C++, and that takes the content either from the local storage or from the Dash client, and then it goes through a pipeline to demux the different streams, video stream or metadata streams, The video streams are decoded with 2D video decoders, so it can rely on the hardware HEVC decoder available on the device. And then there is a synthesizers for each codec to actually reconstruct the 3D representation of the video. So either a point cloud or MPEG immersive video. So what is implemented and available on the tools? Actually, we have two repositories corresponding to these two main components. So a Unity package, which is a RT Unity player, is provided, and it enables the rendering and the interaction in real time with the video. It's a simple application for test and visualizing the content. And this player relies on the decoder plugin library, which currently supports VPCC and MIV codecs. For MIV, there are two profiles, multi-view plus depth and multi-plane images that are supported. Also, in the decoder plugin, there is support for Dash, a Dash client that supports V3C bitstream. So this is a high-level view of the different components, and a bit like the same feature, but from left to right. Here you have the content generation with encoders. Then typically the segments are for CDN are put on an origin server so that they are available. They go through the delivery network, and then we have this on the end devices. We have the platform, the immersive video platform that can be used for decoding and rendering on the end devices. So today, these two repositories are available for early access. So please, anyone can request access. You don't have to be a 5G-MAG member for that. The plan is to go public at some point during the year. We don't have a date yet, but we hope it will be in a few months. And in addition to these two components, also provided in the repo is test contents, so that anybody can try the decoding with and validate that is working. So provided today is a VPCC test content. So it's the sucker, red sucker that is encoded using the reference test model, release 24. We also have a test content for MIV multi-view plus depth, and a test content for multi-plane images. So the two content, the Soccer Red and the DenseB, are content that are natural content, so they are captured with a camera and real actors. And the one on the right is to give an example of CGI content that is recorded in Unity and using virtual cameras to use the same test model. So I'm almost at the end of the presentation, just to give an overview of what has been recently done. So as I mentioned, the initial version, I think it was around June last year, that was provided with the decoder and renderer for VPCC bitstream, and it's according to the MPEG specification. Also support for MPEG-I bitstream with local playback. Then we added the support of MVD with Philips to support the MVD bitstream, and also InterDigital added the support of carriage of this 3C for the Dash client. First for Windows, and now it's running on Windows and Android. And currently we are actually making updates on the tools and making it easier to install. So recently, actually yesterday, we pushed a new version, v0.5, that supports some error handling to check that there is no issue on the network access and also the test content. So here is another view of the architecture that you see that you have the Unity player, and for the decoder plugin, the different components. So if you have an interface basically for local access or dash server access via the client, the native decoder that will demux and decode the different streams, and it will use different sensitizers to reconstruct the different volumetric video. So one for VPCC, one for MID, and one for VD. And these synthesizers are using the reference models from MPEG for parsing the data. I mentioned here some possible direction for next steps. So we are currently working on adding the supports of MPEG haptic, on also dash haptic in the platform. So in yellow here, you see that for that we had haptic decoder and haptic synthesizer that will use the MPEG haptic reference model. And here are possible ideas of improvement, and of course contribution are welcome. And we think that it would be nice to have support for real-time protocols such as RTP. Also, the platform can be complemented with additional synthesizers. So, for example, a synthesizer with mesh coding. And for the application, today what is proposed is a test application, but advanced use case could be implemented in the Unity part for augmented reality or more XR use cases, and also support for new devices like MetaQuest or stereoscopic devices. And this is my last slide to conclude. So these are links to the 5GMag website and also the tutorials. And this is a link to a video that was recorded from a previous 5GMag reference tool call, where there are more details on the standards and the implementation if needed. And yeah, this is my next slide.
Perfect. Thank you, Patrick. Before we move on to the questions, let me highlight one thing again. If you want to try this out yourself, go to the 5GMag website. I'm going to put a link in the chat again. You can request early access. So this is currently all set to private. You won't be accessing that without our permission. But if you go to this form that I just pasted, you can ask for access, and then we're going to grant you access. All right. So we have a lot of questions in the chat, and also Richard has his hand up. I tried to put everything in the right order. Thomas was first. Thomas, should I read your question, or do you want to ask it yourself?
I would be able to ask myself.
Go ahead.
I just wanted to check on the video decoder. So, Philippe, thank you. There is this using basically, but you need to basically decode multiple components. So, are you using multi-video decoders instantiation, or are you muxing those into a single bit stream and using tiling and so on?
So today, the profiles that are supported is the one with multiple videos. So, for example, for VPCC, there are three video bit stream. So we are instantiating 3 video decoders. And the same,
okay.
Maybe.
Okay, and there is no issue of those competing resources or synchronization and so on of the outputs.
Actually, no, we don't have any issue with this. So the 3 bit streams are sent to the video decoders, and then at some point in the what we call the pipeline, there is a scheduler, and each frames are sent to the synthesizer for reconstruction.
All right, thank you.
Thank you. Richard, next.
Hi, yes. Thanks for the talk. Yeah, very interesting. I'm pretty ignorant on a lot of this technology, so apologies in advance if this is a pretty naive question. But you mentioned this idea of packaging these immersive codecs into MPEG-dash. Presumably, this is for kind of on-demand consumption of the scene, as it were. And I'm assuming that maybe you're using ISO-based media file format in those dash segments that you're hosting and serving up from the web server. I'm just wondering what exactly is the scope of each media segment in the dash presentation, and how does that kind of map into the world that we're familiar with in linear audio video, 2D world, adaptation sets and representations. I mean, is it basically the entire video asset in a single dash segment, or is there some temporal division? How does all that map?
Yes, so I'm not an expert on that part, but yes, you are right. So it's the video bit stream, the V3C bit stream is encapsulated in ISO BMF format, and then for the segmentation, in fact, the different components are segmented with. So typically, we are segmenting with a segment of one GOP. And after the segmentation, so as Thomas said, we are using 3 video-based stream. So the output will be, instead of having for 2D, like one GOP, a sequence of a segment of one GOP for one video, the output here will be 3 times these segments, and also a 4th additional track for metadata, which is actually information that enables a reconstruction of the 3D video. But it follows the MPEG-dash specification, so it's M4S segments. So I hope it answers your questions.
Yeah, I think so. Yeah, so am I right in thinking that the even though it's 3-dimensional video, it's still following a linear presentation timeline. So even though it's modeled as maybe a point cloud or whatever your codec is using, it's still following a fixed following a fixed linear playback sequence, and so you just watch it passively.
Yes, actually, so this is the principle that is used for these MPEG standards in V3C, that it relies on video compression. So I didn't explain the process in the encoder and the decoder, but basically it takes as an input a different format like a point cloud or MIV, and these are mapped onto real 2D videos. So 2D videos that will embed all the information needed to reconstruct on the other side of the volumetric video. So it can be typically you have a texture video and also other video for information on the depth or the occupancy. But there are real 2D videos that can be encoded and decoded with existing, for example, HEVC decoder in the platform. And there is a 4th stream for metadata to explain the relation between this video that is transmitted together with the video. But yes, yeah.
Oh, great, thanks.
Okay, and to finalize this, there's also a comment by Bart in the chat. So there's a mapping from V3C to ISO BMF and dash, and you can do it single track or multi-track way. So that emphasizes what we just heard from Patrick. All right, let me scroll up again. So we have another question from Mario. For media delivery, do you plan to add support for other protocols like WebRTC Quick?
So in fact, there is an ITF draft for support of V3C over RTP. So it is currently a draft, and I don't know for Quick, but it's possible, yes. So when I was talking about possible next step for RTP, it would be I think the idea to rely on this ITF draft.
Mm-hmm. And then final question: have you considered integration with or compatibility with WebXR W3C for web-based immersive experiences? Sorry. So basically compatibility with WebXR coming from W3C for web-based immersive experiences.
So to my knowledge, no. For now, as we are using OpenGL for the 3D part. I don't really know the details of WebXR, but that would maybe be possible, but with some work. Yeah.
All right. Thanks, Patrick. That was really interesting. We had also good discussion here. So with that, I would move over to the next presentation.
Thank you.
This is coming from Aljosa and from Kit Jung. It's about VVGLTF, efficient streaming of volumetric video with GLTF. By the way, you guys are killing me with the titles. Okay, Aljosa, go ahead.
Good, thank you. Nice to be here, and thanks for this opportunity to show you some of our work. I hope you hear me well and see this.
Yes, we see your slides. Perfect.
Right. Very good. So this is something that emerged as part of our EU project Transmixer, where we work with almost 20 partners on XR solutions for creative industries and have a couple of creative use cases that make use of volumetric video in various ways. And we kind of looked at how we can exchange such data and make sure they run across different platforms, mainly game engines like Unreal and Unity, but also WebXR and OpenXR and such things. And in particular on mesh-based volumetric video. Right, so quickly an overview. Yeah, so I'll give an intro and examples. I tell something about content creation of volumetric video, and then lead into pipeline and formats, and then present what we did with this VVGLTF extension. So it's basically the same presentation I gave at IBC in September. So I assume you are familiar with this, what volumetric video is. So typically captured with some synchronized setup of cameras that capture, for instance, a person doing some performance and then turn this into some three-dimensional representation, often such a mesh with texture, but also point clouds or Gaussians and other types of 3D representations are possible. And once you have that, you can use whatever you want with, you have a 3D asset and you can use it in XR applications. Here it is a Snapchat filter, or in games, in media productions, or wherever you want to do it. So it's basically 3D digitization of real world environments and people mostly, and then being able to use them in the computer graphics world. Here you see an example also. Yeah, a person wearing a VR headset, exploring a VR environment, and there is a couple of such volumetric video examples, so full 6 degrees of freedom representations of humans. You can also think of it to bring real people into XR, right? So through these approaches, so a showcase of different examples of volumetric video in VR. Or here, two more examples in a project we did back when I was at Trinity College with Trinity Library, one of the famous library of Trinity College, where we, on the right side, you see a 3D reconstruction, a photogrammetry structure from motion reconstruction of the static library itself. And then you see an actor that we dressed up as a historic figure and next to his bust. So that is Sir Jonathan Swift acting next to himself, and having the ideas to virtually visit a place, a museum, and then being able to meet real people in such an application. On the left side, you see the same asset, also the same volumetric video, also created quite a while ago, so the quality is maybe not at the standards we would want to see today. But at that point, it's filmed through a HoloLens, so that's in the real library, and you can imagine this type of cultural heritage applications, person visiting a museum, and then such a volumetric hologram would appear and talk to you. Or here an example, you saw this guy before, also in the context of a cultural heritage project. So people visiting a museum, in this case, a castle, and this is a person, a former owner of the castle, and you can then visit the person in AR. Or here you see a couple of AR examples through a Magic Leap. Yeah, also the example virtual tour guide. Or as it is 3D content, you can also put it on 3D displays, as in this case, these are looking glass displays where you can see such holograms of real people then also appearing. This example was where we worked with a local museum of arts and captured a couple of the actors, not the actors in this case, of the artists, of the painters who created these paintings, and made an app where you could then, with your handheld, go to these paintings and the person would appear and then tell something about the painting, like you see here, right? So this is an AR trigger. And now the painter would appear and give you an enhanced museum experience. So these were kind of application examples, ideas where we use that in real projects. Regarding content creation, most of what you've seen is captured in dedicated studios. I'm also co-founder of a startup in Dublin called Volograms, where we also run basically a web service where you can capture a performance in your studio, right? So this can be affordable studios like ours with only 12 cams, but also high-end studios with 100 cameras and other types of sensors. But the principle is, again, you have these multiple video signals and other data, and you turn it into a three-dimensional representation. So we are not running a studio with Volograms, but kind of a cloud service. Yeah, so the capture can be done anywhere. It's agnostic to the capture. It's transferred to the cloud. Then these algorithms are running. And as a result, you get this asset returned as a 3D asset in a certain format. And here is where formats and standards come into play, right? So because this is most of these reconstruction studios and are creating some sort of a textured 3D meshes, dynamic 3D meshes that are then delivered to the customers to be integrated into the game, the TV show, or the XR application, and so on. So this is the high end of content creation, which is, of course, location dependent, right? So you cannot capture easily in the wild, and it's quite costly and a high effort. Also logistically, you have to take your talent to London or so to Dimensions or to one of these studios and then to capture. So there are also approaches based on latest AI algorithms to get away from this type of capture, to be more affordable, to capture with less complex hardware setups, and also to be able to do that on location in the wild. So that's also what Volograms has developed, but there are many other algorithms, similar algorithms as well, that are able to take maybe even just one image or one monocular video sequence and then turn it into a three-dimensional representation, such a volumetric video, right? So here you see examples of a monocular 3D reconstruction, and then things that users have done with the corresponding app that is available on the iStore. But we also did some professional projects with that type of capture. For instance, in an accelerator project of the IBC 2 years ago, we worked with Fox News and with RTE, the Irish broadcaster, also taking some of imagery and turning it into such 3D assets, and then being able, for instance, to use it as 3D elements in virtual production and other types of professional media productions. So the story here is, no more massive capture studios, but rather affordable setups. And I think what's also important is mobile setups. So it must not only be one camera, it can be a number of cameras, but being able to go and capture in the wild and do the capture on location is something that is very important, and which is also the subject of our own current research and development at Hochschule Luzern, where we look at really capture in the wild, not with one camera, but maybe with a couple of cameras. If you're interested in doing this yourself, you can download the Volu app from the store and do your own captures. You can export the content. There are plugins for Unreal and Unity and so on, and you can use it in your own applications. But you can also capture whatever you want with other cameras and work with holograms also then to get such content and use it in your applications. So here is an example of an anchor person of the Slovenian television captured with a single camera. You see the background, the back of is fully Gen AI, so there are of course limitations to the quality compared to the high-end studio use case. But depending on the scenography and the use case, there may be applications where that is also interesting. And the background that you see here is our lab room represented as a Gaussian splat, right? So also as a kind of AI-based 3D reconstruction of this static environment, and all of this rendered in a Unity scene. So then let's come to the formats and standards and what we did with GLTF, right? So there are, of course, various ways of representing such content. So generally, it is geometry and appearance and maybe additional data. So geometry and texture, but it's dynamic, it's changing over time. Like in this example, you see, for instance, there is a texture atlas that is associated with a dynamically changing 3D geometry, and you have to put those two together in your target application then to do the corresponding 6 degrees of freedom rendering. So this is then a possible representation, like a video, like the one you see here, plus some sort of dynamically changing mesh geometry. But this can still be a lot of data, right? So if the unconstrained reconstruction algorithms can give you something like a super high poly count with gigabytes of data per minute, you can downsample without visual loss to some extent, but it still remains a lot of data with a lot of irrelevancy and redundancy. So there's a big room for compression, as I know many of you are looking at that, how this can be further compressed and transmitted more efficiently. If we look at the pipeline, right? So the classical the media delivery pipeline from acquisition and processing and display, maybe that is the part in the computer vision, computer graphics area. But then also compression, streaming, and also quality assessment are certainly topics that are gaining more and more interest. Here you see an example of compression of such a content with degrading visual quality. And also the quality assessment has to take into account somehow that it is 6 degrees of freedom content and that it's interactive, right? So quality metrics are, for instance, considering such orbits around the scenery as you see in this video to capture somehow like visual quality. So we also released a data set that can be used for evaluations where the content is also available as meshes and point clouds. So there's also comparative studies possible, like the one we did here back then, because there are various ways of thinking of volumetric video. So one is the classical computer graphics approach, right? So you represent the geometry as a 3D mesh and the associated texture. You have something like a texture atlas, vertices and faces, 3D geometry. It fits into the node thinking of and the philosophy that we find in graphics. And the other one is maybe thinking it rather of, you have a video, you have an array of pixels, and then you turn it into the third dimension, then you get 3D points, and it's more like a stream, a timeline moving points in 3D. So it's more like coming from the philosophy from the video side of things. But in the end, both are equivalent if we just think of that we want to render output images at certain arbitrary viewpoints. So the question of which representation and then associated compression, streaming, and so on is one that is obviously still matter to the application, and not really resolved in that sense, right? So what we have been looking at is at mesh-based representations in this work, because that is what our setup, our applications with Unity and Unreal and are mostly looking at. Also being able to integrate the content into bigger applications where you need collision, you need kind of some of the functionalities that you don't get easily with point clouds, but easier with meshes. And we looked at GLTF as it's kind of emerging as something like the equivalent of JPEG for transmission of 3D data in an interoperable way. So that's why we came up with the idea how to manage volumetric video in a GLTF. And as you see, GLTF comes from the graphics side of view, the philosophy. It's a node-based scene description format, right? Where you have your objects represented in such a tree with inheritance of these features. And kind of a video with a timeline is a little bit something different. And to bring these two worlds together is not so easy often. And what we did for that is to define this GLTF extension, which is basically a controller which stores the meshes belonging to the corresponding sequence and the textured stored as a video. And then in the player, they are updating the mesh and the texture in the corresponding node, and then being able that the GLTF mesh is being played back in the scene with these corresponding updates that, of course, have to be synchronized accordingly, right? So that is the basic idea of the GLTF extension. And then you can also build that. You can make chunks of such GLTF files corresponding to a couple of files and put them together. And then a kind of a whole program or a live streaming of something can then be kind of a succession of such GLTF chunks that can be then also transmitted via standard infrastructure like HLS for the video, or GLTF streaming. So we built a demo system with a client that would access such GLTF files from a server, and then being able to play them back accordingly. And in terms of evaluation and efficiency, we looked at one thing is so the raw data that we have is basically the meshes and the video and the textures, and they have to be transmitted. In order to put them together and to stream them, we have to add a little bit of overhead to that. And this overhead, of course, adds additional data. So you want to minimize that. So you want to make your chunks as big as possible. So to minimize the relative overhead that you add there. But on the other hand, a long chunk introduces a delay because you have to wait until the chunk is full before you can transmit it. So there's kind of a trade-off between delay and overhead that we wanted to look at. So we took for some of these sequences 300 frames, and we chunked them into from 10 seconds, like all 300 in one piece, in one GLTF file, to subdivisions down to a single frame. So that means then 0 latency or 10 seconds latency. And we basically measured the file size that we get there first for uncompressed geometry, and we found that the down to delays of below a second, which corresponds to standard video GOP sizes, the overhead is negligible. And then we did the same with Draco compression, which is something which is natively supported by GLTF, right? So we compressed the meshes with Draco. non-dynamic, no redundancy yet at this point. So just mesh by mesh as Draco supports it. And here you see also, yeah, that first of all, we can get the data rates quite down, right? So this is now compared to what was here in the raw data rates, a factor of 10 or so, which was compressed. But on the other hand, also the delay is negligible, right? So this seems to be something which is suitable for transmitting such volumetric video over GLTF to browsers and whatever. And so for the video compression of the textures, also any video codec can be used. So we just use some standard MPEG codec for compression for that. Yeah, and this was made available. So if you are interested, you can download it and use it, try it, and happy to talk to you if you have any further ideas or questions. And also, the full technical paper has just been published in the SMT Motion Imaging Journal these days. Yeah, and that's it, basically, right? So,
thank you, Aljosa. Do we have questions, comments? So maybe I start. So you showed all of this capturing at the beginning. I was wondering, and this is probably a very naive question, but is that possible in real time that you do the capturing and afterwards the encoding, the packaging, or whatever comes afterwards, so that you do like a live stream, all of that?
yeah, it is possible. It depends on the capture method that you use, but there's certainly a connection between quality and trade-off and real time, right? So if you do it offline and with a lot of cameras and in a high-end studio, you will get best possible quality, but it will be least real-time capable. If you use something like a depth sensor or multiple depth sensors and have a reconstruction algorithm that is capable to turn these in real time into a 3D representation and stream that, that's also possible. So real-time systems are available, but it's a field that is very multidimensional, and there is no clear, each system that is out there and described somehow uses a certain sweet spot in this kind of tension between real-time quality, complexity of the system, meshes or point clouds and all of that. No, but there are real-time systems.
Okay, basically what an encoder, yeah.
One famous one is the Microsoft holoportation, right? So where there's real-time communication has been demonstrated. Yeah.
Perfect. Then we have Thomas. Thomas, you're muted.
No, very interesting. Thank you. First, a question: are you aware of what we did in MPEG, the scene description extensions? Because basically that is, I believe, more or less equivalent to your extension. So there is MPEG Media, there is the ability to basically stream into GLTF, and I think that is very similar. I'm just checking, are you aware of this? And that's part of the extensions also implemented in the reference tool. So it would be great to harmonize this, right?
Yeah, so we are aware of this, but I mean, these things are for us quite massive and not easily accessible. So it was a little bit kind of a pragmatic approach to something that is quite easily implemented. So this extension is not a massive thing, but something that works quickly and easily. But we are aware that there is a relation to what you have been doing in MPEG, and we have been reviewing these things as well. Yes.
Okay. But that's fine. I think it just should harmonize this a bit also towards the presentation, because I don't believe it's good that there is too many extensions that are doing similar things into GLTF. I don't know if those years have been adopted or reviewed yet. I understand it's a pull request at this stage, which is good to harmonize. So second question is more about, I understand, so we're looking at this production, and it's good that you guys look into more user-generated production and so on and so on. The question is just, if you do things like this digital inheritance and is it not easier to basically capture, get to a full
avatar model and then do animations, because then you can do a lot more things. You can use the same person, you can animate instead of going through dynamic meshes. So that approach seems to be more, it doesn't change that you need to capture once, but then you can use and animate rather than basically going through a production chain. For every scene that for 30 seconds, you have to have a production setup, speaking, and then the amount of assets will just not grow. So we just don't see that these dynamic meshes or particular point clouds that we get a huge amount of data assets that would worth it to basically go and implement this on mainstream devices.
Yeah, so that's a very good question. So this is also something we are actively looking at, and we had some projects where we compared exactly that, right? So on the same content, scanning plus motion capture and animation playback versus volumetric video. There are the quality of the animation hasn't been at that level to everyone available yet, such that you could think of a photorealistic, believable human representation. So there would be cases where, so with the latest MetaHuman and other approaches, AI-based facial animation techniques, we are getting closer, but there is still something like an uncanny valley effect with regard to animated humans. And in some cases, it is rather the believability also plays a role, where you really think this is the person and it's not an animated character, right? So it's a question that has a lot of dimensions, and that also with different use cases can be answered in a different way. But I believe that also going further down and being able to do really 3D capture and reconstruction in real time at a high end of quality, such that basically myself and you, we are in this video chat as kind of a three-dimensional representation of ourselves. That will bring the usefulness of the volumetric capture further closer to everyone's use.
Yeah, I don't want to use all the time, but there's also the question, the capture, for example, if you would go into the 3D space, you would wear an HMD, right? So then the HMD, you would have to capture a person with an HMD, which would be weird. So that's why the Zuckerberg interview, for example, there's like 3 minutes, is something that shows. So the avatar has benefits here, right? So I mean, I understand this needs to be researched and discussed. I'm just checking if you have looked into this approach as well. And Imed has a presentation later that speaks about these animated avatars. Thank you.
Yeah, no, it's
Okay.
a central question that we are very much interested in to look at. And of course, with the improvement of metahumans and other types of avatar recreation techniques, these differences become more and more subtle and yeah, interesting. Yeah.
Okay, this is a good point, Thomas, because we are running a bit out of time today. Thank you, Aljosa. I would ask you to also check the chat. We have at least one more question from Marius in the chat, so that we maybe discuss this further in the chat so that we can come to the next presentation now. Thank you again for your presentation. With that, we have officially 15 minutes left, so we will definitely run over time. I was asked if Mario can go next. So I want to check with Imed if it would be okay, Imed, if Mario presents now, because I think he has to leave in time, and you would go afterwards. Is that okay for you?
Yeah, that's fine.
Perfect. Thank you. Then
Okay,
Mario, you're up next. I'm gonna try to read your title. That is a challenge for me, but I'm gonna try. So it's our developments. So
no,
yes.
I have simplified it. No worries.
Okay, then
I can.
I'm gonna leave it to you. So you're saving me here. Okay, go ahead.
Okay. Let me check sharing the screen. Can you confirm you can see my screen?
Well, we see the slides.
Okay, so I have simplified the title, so it's Researcher Network and
Okay.
Volumetric Video Services. So
All right.
thank you very much for letting me and inviting me for the presentation and letting me to be first, because I need to take a flight at 5 from Finland to back home. So yeah, this is Mario Montagud. This is a researcher at ITUCAT and the University of Valencia, and this talk is about giving a high-level overview of the research we're conducting from I2CAT on networked volumetric video services, okay? So this is roughly the agenda. So we will briefly present us what is our vision and the scope of this talk, and then we will concentrate the topic today on real-time holographic communications, okay? I will skip the last topic because otherwise we will run out of time. So yeah, I see some colleagues on the chat, but basically I2CAT is a research center based in Barcelona. We are over 250 researchers around different topics around advanced digital technologies, and I belong to it's mostly 5G, 6G, artificial intelligence, and I belong to the Department of Immersive and Interactive Technologies. And we are quite active indeed in research projects, European projects from the XR and the 6G domain. Okay, probably you are quite familiar with some logos, such as XR Echo, Presence, or HIT projects, or in the ZenX project, 6G XR, Sunrise 6G. Okay, these are just some examples. So yeah, we have discussed in previous talks about capturing in real time humans, no, with affordable setups. In our case, we're focusing on affordable capture setups using Azure Kinect or back cameras, using both a unique camera that captures your frontal viewpoint or multiple cameras, okay? So the result would be what we can see in the image in the center at the top, which is a 3D Gaussian splatting reconstruction of an environment. In this case, is a room of I2CAT, but here we can see our colleague Stefano captured therein, okay? But we could also, like in the demos that Aljosa shown, project a user in the real environment, okay? Like a teleported hologram sit on a chair next to you, so if that user were there. Okay, this is already nice, but what if we want to enable real-time communications between multiple remote users? So this is the figure that we show on the right, in which we teleported we will see a demo video about this, okay? 5 users in real time from their home to a shared room, no? In this case, a virtual round table, to have like a meeting in the holoverse. Is that like the next generation of video conferencing? Like if we were having this meeting today in a metaverse-like scenario. So this has been or is being our main research topic in the last years. And you can imagine, no? If you want to address the end-to-end chain, there are a lot of challenges. So one is volumetric capture and reconstruction. So we have talked, okay, what kind of sensors or how many sensors? Yeah, this is an issue. Volumetric video compression, we have talked today about different codecs that there are. I will introduce in the next slide a new approach that we are tackling today. And we are also interested in how to enable, in 2D video, adaptive video bitrate streaming is a well-established topic, but in 3D video or in volumetric video, maybe we could do a little bit more, no? I will introduce later some things that we are doing in this domain, and also on how we can enable volumetric video streaming. That's why I was asking before about protocols or many-to-many scenarios, such as to enable real-time communications. And then it's also quite aligned with what 5G MAC is doing or wants to do in exploiting the capabilities of next generation networks like 6G to use network APIs that can allow us, for example, to recommend data rates for the end users or to use edge cloud APIs. For those who are not familiar with these APIs, I will show some examples later, okay? We have been focusing on point clouds until now, but since a few months ago, together also with Aljosa, we're exploring the 3D Gaussian splatting, okay, and the capabilities for more nicer or more high quality reconstruction and to explore the limits for near real-time performance. So yeah, let's talk about the work we are doing on holographic communications. And for this, I'm going to first introduce our Holomid platform. Holomid platform is a platform that we developed in the VR Together project. And let me show you a demo video of the scenario that I described just a few seconds ago. So it's the figure on the left, because I see the figure on the video. yeah, stop this one. So 8 users connected from different cities in Spain, they're having a virtual meeting in real time. In this case, this is a point cloud codec, the one developed, the open source by CWI in VR together, okay? And the latency is around 120, 150 milliseconds, okay? Using a SFU, a selective forwarding unit distribution mode. So this was the limit. So it's not the best video in terms of quality of holograms that we have, but we love it because it was the first time we saw 8 users together in a shared environment. And now in HIT project, together with Aljosa, we're exploring communications in more hybrid XR environments in which you could be in the, as I now know, in a room with a sofa next to me, and I could see teleported a colleague from another part in the world as if that colleague was there. Okay, so we can have like virtual meetings, but not in the metaverse. We're still in the real environment. So what you see in the real environment is the 2 different rooms from InterDigital, but you see a colleague indeed sit on a chair or on a sofa next to you as if you were there together. Okay. So to give you, I will share the links of the videos later, but yeah, for example, this is the view of a third user seeing a real user and an holoported user. So you can see that still the quality of the reconstructed hologram in real time still needs to improve, and we are working on it, but it already gives the feeling that that user is there and you can identify him or her, okay? So these are the scenarios we're trying to enable. So let's see some of the challenges we're tackling, okay? In terms of the volumetric video pipeline, I cannot tell that much, but what I can say is that we're following an approach similar to the video-based point cloud compression, in which we project onto the video and the depth as a position map, and then we convert geometries into colors, and that way we can exploit to the video codec like X264 or X265, okay, and exploit the capabilities of the GPU, no? And in this case, by doing so, we can also perform in real-time rate adaptations by adjusting, for example, the CRF or the quantizer values, or leverage interframe redundancy, okay? While still, I mean, it has an impact on the real-time responsiveness, but still give very good performance in terms of latency. And you can see in the SIF, I don't know what, yeah, that the quality that we get, this is with one camera, okay? So just capturing the frontal viewpoint of the user, the quality is already quite good, okay? I'm saying that I cannot tell too much because next week and the other, we are performing tests comparing with other volumetric video pipelines, so we will be happy to share the result once available, okay? So if you, if we want to enable this kind of scenarios with multiple cameras and multiple users, I guess that you are imagining, okay, but you need super complex and expensive clients, client machines, and also servers if we want to perform transcoding on the cloud. Yeah, and that's true because, for example, on the production side, you can have like multiple cameras. This can be, for example, we are testing with 3 or 4 cameras to capture a full volume in real time, but then you need to fuse the streams, reconstruct the volume in real time, encode the volumetric video. And imagine that you are having a video conference with end users, put, for example, or let's put N is 4, then you are receiving in the downlink 3 streams from the other users. So you need to receive their streams, decode them, compose the scene, and render it. So at the end, you can have a headset, but it's a headset connected via cable to the PC, no? So you need a PC with GPU capabilities. And you could think, okay, we could implement an MCU for volumetric video, what we did in 2 years ago when we presented this at ICM Multimedia. We'll give the reference to that paper. But still, you are receiving a big stream in downlink. So having untethered an application on an untethered device is still a challenge for this kind of applications, okay? So what we are doing in our current project is try to offload some processing functions, from processing functions from the clients to the edge, and also to bring some computation power from the cloud, statically deployed there to the edge, so thanks to a cognitive orchestration, So we bring the computational power as close as possible to the client, okay? So we have like a deployment over the cloud continuum, leveraging the 6 or the next generation smart networks. So that would be the result, and you can see, wow, this is too much abstract, too much information, but let's see some examples, okay, of the technological assets that we currently have. So the first one is, Aljosa has shown some examples of volumetric video capture setups in which we see a lot of cables, no, and they are very expensive, they are complex to set up. So what we would like to do is, okay, let's try to minimize the usage of cables. Let's try to send as raw as possible streams to the edge and let the magic happen on the edge, okay? And the magic can be different things. Whether we are using like light field sensor, we're working with different companies like Raytrix or Woodpeaks, no? Who are light field manufacturers. We're also working with UPM, the Polytechnic University of Madrid, with the live free viewpoint video system. So yeah, depending on this, but what we want is try to minimize the cost and the complexity on the client side by leveraging edge computing. And of course, if we want to do this, we need the 5G network to provide you high uplink capacity and very low latency, okay? Here you have a video of the work we are doing with UPM. I will skip this and we'll share later the slide with Jordi, and you will have the details. But you will see that the quality that we achieve with live free viewpoint video is already quite good. Still, you need 9 sensors. No? In this case, this setup is with 9 Z cameras, but the quality is already quite good. And I think the latency is around 300 milliseconds end to end, which is quite acceptable for real-time communications. For our point cloud pipeline is lower, but still you have this asynchrony between different media modalities, but still the experiments we're doing is resulting quite acceptable user experience. Yeah, another topic that we're working now is, okay, but what if I want to join this metaverse sessions from a lightweight player? So I don't have GPU or I don't have high bandwidth. So we're working on remote rendering, and in particular in 2 versions of remote rendering. The first one is, imagine that we're having this workshop on the metaverse, and we want to broadcast or deliver it to the mass audience via 2D video or 360 video. So we could deploy like another client on the cloud, and that client sending using Dash or HLS a 2D from a fixed position, and it could be or viewport, or it could be a 360 video. We could deliver this stream to the mass audience. Okay, so this is what we call one-to-many remote rendering. But it could also be that, for example, Aljosa, Jordi, and me are having like a meeting in the metaverse, and for users, for example, Daniel would like to join. So we could deploy a remote renderer specifically for Daniel close to him, and Daniel would receiving a rendered stream from his viewpoint and his particular position in the metaverse, while still being able to talk with the others and freely navigate, having 6 degrees of freedom. So let me show you a video of a demo we showed at the 16G event together with our partners Bicomtech, a research center in the Basque Country. So this is the web browser using WebXR. And yeah, you can see the colleague Roberto Viola renders the point cloud stream from a remote native client. So you are using a web client, but still you could talk with to Roberto or freely navigate around the virtual environment. Okay, so you are leveraging all the interactivity possibilities that a native application is giving you. And the figure or the video on the right shows that by using URS is the Unity Render Streaming plugin of Unity, we're able to achieve like delays of 30, it depends on the resolution and the network, okay? And we have also tested with different protocols. That's why I was asking before about protocols, but the delays could be range between a few tens of milliseconds or 150 milliseconds, okay? Depending on the configuration, but this is already quite good, okay? And the resolution is 4K, okay? Also, if you are using a web browser, you also need to adhere to what the web browser can decode. And let me go to the third enabler, or third kind of enabler. You all know, that if we are in a 3D environment with 6 degrees of freedom, you cannot watch at any moment all the information, but only what is inside your field of view. So there could be some holograms that are not visible at a specific moment, or some holograms that are far away, no? So you don't need the same resolution for the users that are in the virtual world, like 1 meter distant from you, that for other users that are, I don't know, 20 meters away from you. I know that the community is doing some work on cubic segmentation as done for 360 video, no? Or on projections. We also implemented like a multi-point control unit for volumetric video. So the details, this is the reference of the paper I was mentioning before. But let me show you some enablers that we're trying to deploy in SNS projects. So the figure on the left shows that client 1 could have like client 2 in the central part of the viewport, client 3 and 4 on the peripheral part of the viewpoint, but more far away, and 5 and 6 outside the field of view, okay? So you could implement like advanced or strategic, I would say, more than advanced, delivery methods using selective forwarding unit, in which you simply don't forward to that client the volumetric streams of the users that you cannot see, okay? Or for example, for those users that are far, you could dynamically instantiate transcoding instances in the cloud. So you provide, for example, for client 3 or 4, lower resolution volumetric video streams, okay? So we are currently implementing this. We have proof of concept for 3 users, and it was quite well, okay? Quite in real time. And the second enabler we're trying to adopt, and this is related to the camera APIs, is imagine that, I don't know, Sergi, Aljosa, and I are in Valencia, no? And we want to have a holographic communication meeting. So if we have different edge servers, let's be smart and choose an edge server close to Valencia, no? So we need the network to tell us, okay, guys, you are in a geographical region, so we will select this edge server for you. Or imagine that we want to have a holographic communication session with 10 users, but the maximum capacity for a single SFU is 8 users, for example, because you can see, okay, the SFU doesn't need to transcode, so it doesn't perform advanced processing function. But the bottleneck, for example, when you deploy it on an Amazon Web Service or on Azure, is the downlink bandwidth, because you're sending n-1 streams to the n clients, okay? So we are also testing on having more modular architectures, leveraging or having like distributed SFUs. And I will show a video showing that this increases scalability, a video at a graph. Or we could also perform transcoding, which is the image that I showed, or the diagram that I explained a few seconds ago. So some results, they are recent results, and we are trying to publish this in a journal this month. The graph on the left shows that, for example, in one SFU, using particular instances of Amazon Web Services, with the bottleneck, the scalability bottleneck or limit, better said, was 9 users, okay? But if we deploy like 2 or 3 SFUs, as we don't increase the bandwidth limits in the downlink from that the hyperscaler is giving you, we could achieve more than 15 users. And this is quite particular what happens, because you are receiving different delays, not symmetric delays for the clients, depending on the SFUs they are connected to. But still the differences are, they are quite within acceptable limits to the human perception, we could say, okay? Yeah. And then the image on the right shows that, the video, sorry, on the right, shows that by performing the viewport and position-aware strategies, delivery strategies, we support the scenarios up to 25 users, okay? Of course, this depends on the specific networks and the machine that you are running, but with a machine that without these enablers supported 8 users, we are able to support up to 25 users. These are pre-recorded holograms, okay? They are not so nice. We just use them for testing, and we are sharing this with you. But we want to prepare a nicer video for demonstration purposes with nicely captured holograms. Yeah, and we're already finalizing. in 6GXR and Sunrise 6G SNS projects, we are working on network as a service architectures and APIs to try to improve the interoperability and the performance of XR services. Okay, we are focusing our use case on holographic communications, but it could be everything. So we are working on two main types of APIs. The first one is on providing network-assisted rate control because, there exist different client-driven or server-driven adaptive bitrate strategies, especially in the 2D video world. But what we are leveraging is a network function that knows have a comprehensive awareness of what is happening in the network, how many users, how many services are active, and is providing recommendations of the uplink and downlink rates for each one of the users of the service, okay? Jordi, or everyone, it's quite interesting that we released this quality on demand. Sorry, I'm mixing things. So this is providing rate recommendation to the clients or to media functions, but once detecting quality of service drops or when detecting congestion in the network, we could also let or ask the network to provide quality on demand. And this is the Camara quality on demand API that we implemented for the Open 5GS network that we are sharing as open source. I will share the details, okay? I was mixing things. And the second type of network, the APIs that we are developing is about edge cloud APIs. Because, if you want to dynamically orchestrate network component or network functions over the cloud continuum, it's very useful to have this kind of APIs to be able to discover what edges are available, what are their capabilities, and to be able to onboard your artifact, okay, on the edge server of interest and to manage the life cycle. So there are some standardization activities happening in there, and we haven't implemented them yet, but we're in the process now of finding the use cases in terms of in the context of holographic communications, and try to run use cases and demonstrators, and we plan to run them by this summer. And another thing that we're doing, you could think, okay, but the different operators could have different APIs, or if you are connected to an operator, another operator, what's happening there? So we are working on this kind of enabling cross-domain federation, or using or enabling multi-telco compatibility. So it's having like a layer of abstraction that hinders the complexity of knowing all kind of APIs to the XR service providers. Last slide is we are also because I also think this is relevant for 5G MAC. We are working with companies specialists in virtual production, in this case Brainstorm, in which we integrate this kind of holographic communication service to virtual production engines, which you could have like a virtual TV set with users integrated from a chroma key room in real time, and who are interacting in real time from remote users. And this could be like the audience members that are teleported to the TV show, or they could be also a virtual TV debate. No, there is, for example, Jordi is the presenter, and we are like the panelists, and Jordi is interacting with us in real time, and then we can the virtual production, we can prepare it for the broadcast audience. So we are showing a demo of this next week in the Integrated Systems Europe Fair in Barcelona. So if you are interested, feel free to come. I skip this part, which is basically, as Aljosa said, okay, what you want, we want to capture the 3D environment in the wild, okay? So we could use different sensors, and then you need a huge processing load for reconstructing the environment, or for encoding it and for streaming it. So we are particularly interested in how to encode these large scale scenes, how to stream them in a strategic way, okay? So in this video, we're showing a demo we did for the Didymos XR project, in which we delivered a large scale point cloud to a smartphone. Indeed, it was an Android smartphone. So that concludes the talk. Hope it has been interesting for you. We haven't joined 5G MAC yet, but we are in the process of this, so we will be happy to collaborate and the talks have been really interesting. So I think they will be very valuable for us, the work that you are doing. So that's it. Thank you very much.
Perfect. Thank you, Mario. I think we have time for one quick question so that you also don't miss your flight. We don't want that.
Hopefully not.
Let's check. Thomas, go ahead.
Yeah, no, I can go quickly. I think, I mean, it's very interesting in a way that there's a lot of ambition and challenges. There's just one aspect more as a comment. What we're seeing is that these connected rendering, very complex services are just not the way how people go right now. Look at the AVP as maybe a reference design, and that is completely unconnected, tries to do all of the processing locally. And we're seeing that trend is happening at least with products and services now. So this huge reliance on a network that is stable, up and running, high quality of service, to get a service up and running is something that I believe needs to commercially and user experience wise, has a lot of challenges. So, and while we started with split rendering, we also understand that edge resources today for cloud rendering or edge rendering is a very complex and expensive process. So I'm just wanting to be checking a bit careful in a way that we say we enter in this massive amount of work here, because this still needs to be checked and proven to be feasible and kicking off and then commercially scalable, right? So I leave it at this. I mean, it's probably research-wise, it's very interesting.
Yeah, that's true. I mean, I can say that until the moment we're focusing, there's challenges within the media domain, we could say, or IP-based scenarios. And then we are starting to deploy this in edge infrastructures run by Telefonica and by Capgemini and by Ericsson. And let's see how far we can get, no? But I agree that it will be a big challenge. And yeah, there's a research project. Let's see if we can achieve a high TRL close to product or close to real live service. Hopefully, yes. But yeah, I see your point. This is a big challenge. And especially you want to do this, I mean, dynamically orchestrated based on demand, no? Yeah, I agree.
Perfect. Thank you, Mario. Then please catch your flight. And we have our last presentation for today, which is coming from Imed, from Qualcomm.
Thank you.
MPEG. Thank you, Mario. It's about MPEG Avatar and 3GPP Release 19 studies. Imed, please go ahead.
Yeah, thank you. Let me share my screen. Let me know if you can see it.
It's loading. Now we see it.
Okay, very good. Yeah, so the presentation is on enabling avatar communications in MPEG and 3GPP. It's basically about the study that is currently happening in 3GPP with like a prospective normative work and in SA4, but the work in 3GPP actually started way before that.
Sorry, but your audio is a bit distorted. Are you close to the micro?
Yeah.
So we can hear you, but it's a bit interrupted, at least for me. Maybe people can confirm it's the same for them.
Okay. Give me a second. Let me try to maybe see the settings here.
Charlie, is it the same for you?
Yes, it's a bit babbling, right? The audio.
Okay. Imed, no worries. If it can't be fixed right now, that's fine. We hear you. But as I said, it's a bit distorted.
Is it better now? Is it any better now?
Slightly, maybe. But maybe go ahead. And if we can't hear, we're going to ask.
I might have to rejoin if you don't mind. Maybe I leave and join again.
Okay.
And see
Okay. Go ahead.
Okay.
No problem.
Sorry for that.
All good.
I don't know what's happening to my audio device. So I said this started actually in SA1, and for those who don't know, SA1 is like the group that defines requirements for 3GPP work. And that was back in 2021. So they were looking at how to evolve like the voice or the multimedia telephony service that we have today on all our phones, looking at to giving them or enhancing them with more features. And there are a few features that are coming out that are quite interesting, like running web apps in your phone dialer. That should be starting to be available already, at least in some regions. But one of their enhancement ideas was the AR call or AR telephony for augmented reality, and they set some requirements around that. And avatar is really one of the main features there. So people should be able to communicate with their 3D avatars or the multimedia telephony service that we know. So that was the trigger. And then from there on, SA2, which is the architecture group, set out to like extend the architecture, the IMS architecture to support like avatar communication. Somewhere here you should see the enhancements with base avatar repository. So base avatar repository is really the entity that will store your customized avatar, maybe with some assets like your clothes or garments, any digital assets associated with it. And that will be used then for multimedia telephony or AR calls with your avatar. So the way it works is like this. So you'll join a call, and then one of the participants will start the migration into an AR call. That will trigger the creation of like a 3D scene. Maybe it's a virtual conference room and so on. And then people are there and they move around and see stuff in 6DoF pretty much. So it's a 6DoF experience. So it starts by each participant sharing their avatar or information about their avatar. The other participants will then download that base avatar and start receiving animation streams and rendering it. So what SA4 is doing is really the stage 3 work for that. So we have the architecture in place. We have the requirements that triggered all of this. Now we need to look at how to realize this, and it can be realized by translating like all this functionality into something complete. Stage 2, as most of you probably know, is very abstract. It's just giving an architecture, some procedures. So what we really needed is some format. Like we have this base avatar repository, for instance, which will store the base avatar of users and their digital assets and so on. But what formats are going to be used there? So SA4 has this study to identify like what needs to be done in terms of formats, in terms of protocols. And the first problem we faced is really the lack of any standardized formats for avatars. So we have plenty of like proprietary ones. Some of them are available. Some of them are kept completely proprietary. We heard about MetaHuman and so on with Pixar, with Unreal Engine and so on. But all of these formats are really closed formats. I think MetaHuman started like open sourcing their DNA format, which is just the head, but that's not sufficient and it's not standardized. So that triggered like this relation or this activity in MPEG to address the needs of for a standardized avatar format. The activity there in MPEG is called avatar representation format, and we hope that at least timeline-wise, that the specification will be ready for the 3GPP timeline which will probably be the first customer or user of that like representation format for avatars. The timeline in MPEG is like this. So we are now at CD stage after the Geneva meeting last week, which is a big milestone. I think now at CD stage, people can start reading the spec, maybe even referencing it and using it. And we hope that by end of the year we should have like now how that works. So we heard a lot about like the XR player and MPEG-I scene description. So this is not really limited to MPEG-I scene description, but it's built on the MPEG-I architecture, which separates, as we heard earlier, the media access from the representation. So the presentation engine doesn't really need to bother about like the handling animation streams or like the formats for avatars or the different animation frameworks and so on. So that all is delegated to what we call an avatar pipeline. And the avatar pipeline will feed a reconstructed avatar to the presentation engine. Of course, this is like a reference design, but nothing really limits how or in the implementation and the specification, nothing limits this or realization of the animation framework to a particular way of doing things. So we internally, for instance, we have implemented this based on some ML-based avatar reconstruction animation with splats and so on. So it's very flexible in a way that it only standardizes the left part to the avatar media function. Doesn't standardize how the avatar media function does the avatar animation and in what format it has to pass it to the presentation engine. So that's all left for implementations to innovate. So looking at this avatar representation format from MPEG, so it's quite simple actually. It has the three main components. So a document that describes the different pieces and the sets of a base avatar. So the base avatar can store like not just like the bare bone avatar of the user, but maybe it's a collection of their assets. If they go and in the digital market and buy, say, a suit or a hat or something like that, it gets stored there, and it can be used in an AR call session. For instance, or some other applications or metaverse words. So that document will describe all these assets, and it will provide them also at different levels of detail to accommodate for like different network or like processing scenarios. For instance, when sharing this with users that are limited in terms of their bandwidth, they might opt for a low level of detail representation of that person, or like if they have like good processing power and network connectivity, they will go for the highest level of detail. So that's all supported by the ARF format. Then the next piece is the ARF container, which is really like a container that encapsulates the ARF document and all other pieces, like all the meshes or the assets, all the data like weights and stuff like that, maybe even like proprietary ML models and stuff like that can all be encapsulated in that ARF container. It's indexed by the ARF document. And then finally, it defines the animation stream formats, so the animation samples, which are used to drive that avatar. So we know that there are plenty of tracking frameworks for avatars, like for facial blend shapes. For instance, Meta has their own like blend shape sets. Apple with ARKit has their own, and so on. So we want to interoperate with all of these. So we allow for signaling of what animation frameworks are supported. Of course, it targets also different types of animations like facial expressions, body, hand, eye, and so on. So right now, we have ARF has support for facial expression, body, and hand animations. We're also working on eye animations and looking at other like other types of animations. Maybe in the future we'll get into like more advanced animations like hair and garments and so on. But that's where we stand right now. The main promise of the ARF is that it supports the spatial access. So if I'm a user, I have a container that has all my assets, like all my wardrobe, for instance. If I join a call, I'm not interested in sharing all of that with all participants. So it should be only a subset that I choose. Like today, I wear a hat or something. So only that set is shared with the participants. They should not be allowed access to everything. So that's supported by the R format. Also, like ensuring that or having like anchors or placeholders so that authentication features are implemented to ensure, for instance, that it's not like a different person trying to use your avatar and so on. So that's included in it. So let's get to the animation itself. So the animation, one key promise we wanted to have is interoperability with OpenXR. So OpenXR has like several extensions which do tracking. So you can rely on the XR runtime to give you, for instance, like a set of blend shape weights that you can use to animate your avatar's face, and it can also track your body joints or your hand joints and so on. So it's very handy. It's available already on several HMDs. So it was a natural choice to like have this compatibility with OpenXR. So you don't have to, as a developer, you wouldn't have to like implement your own tracking libraries and so on. It comes for free from OpenXR and your XR runtime. So the animation stream formats are compatible with what OpenXR tracking provides. For facial animation, it will be depending on what blend shape set you're using. It will be set of weights that get like encoded according to the provided sample format, the ARF sample format, and then streamed to the other end, maybe with WebRTC or something else. And then the receiver will like animate the avatar and render it accordingly. And the animation is quite simple, actually. If you would implement a traditional way of animating facial expressions with blend shapes, just like weighted sum of the avatars that determines the location of each vertex of the face. So you will have like your blend shape set, which is stored in the ARF container. Will have like several blend shapes that have the same exact topology, just some vertex displacement, and that gets calculated then through the animation. Of course, you can do more advanced and more natural, like facial expressions if you go for nonlinear machine learning based, for instance, approaches for the animation, but that's like the reference implementation. For body, it's very similar. So you use OpenXR to get your joint positions. You have a skeleton that is tracked by the XR runtime, and you get access to the positions of each of these bones, and you stream that to the other end, which will use them to animate the avatar and its associated or skins meshes accordingly. So that uses a very well-known technique called linear blend skinning. Again, here it's linear, so you can do better if you do non-linear, but that's really up to implementations. Yeah, I think that's pretty much it. So to the reference software, MPEG has developed reference software. For those of you who will be maybe in the next 3GPP or MPEG meeting, you can see demos of that. If you're interested also, I think we can share access to the reference software. What we look forward for is really integrating or an implementation that ports that into the XR player. As you know, 3GPP has defined WebRTC specifications to work over 5G with all like the whistles and bells, like all the quality of support and so on. So that would be a very good use case to demonstrate that. So we would implement WebRTC based pipeline. We saw like the pipelines that are already there for like real-time media. So this could be an extension of that that implements like maybe simple avatar animation to start with. Yeah, so it's all the data can be like exchanged over WebRTC over data channel. We only need the audio data channel from traditional like WebRTC. The rest can be exchanged over the data channel. The tracking information and so on can be fetched through OpenXR, like Unity's OpenXR plugin would be able to provide that. And we can demonstrate a live avatar communication scenario. And we are excited to work on that and hope that this project gets started. We look forward to working with all of you on that. Thank you.
Thank you, Imed. We have 2 questions in the chat. I'm going to read the first one. That is coming from Marius. So he's asking, how much different or similar is the MPEG avatar description from a GLTF representation corresponding to an avatar object in the scene? As example, GLTF supports skinning and blend shapes. Are the MPEG representations for this data different from how GLTF is defining them?
Yeah, very good question, Marius. So it's basically very similar to that in the way that we extracted this functionality to be available at a higher layer. So with GLTF, you can have one asset, one skeleton. We needed more. We needed to support multiple skeletons for different animation frameworks. Like if you could have, for instance, blend shapes or ARKit and another blend shape set for like Facebook Oculus, for instance, or Meta Oculus. So it's really exposing that information to the upper layer. We still maintain like the geometry descriptions and so on as they are. So we reference GLB, which is the binary format of GLTF for the mesh components. But we needed to expose that like skeletons and the joints and the blend shapes at a higher layer.
All right, and then Jody, you also had a question. Is that already answered, or do you want to still ask?
I think it's answered. It was very similar, and I think we can deal with it in another telco and when we deal more with this work. Thank you, Imed.
Okay, perfect. Thank you, Imed. Thank you to all the speakers, and also thank you for staying that long. I know we are quite over time now, So we're going to close this session for today. The recordings will be made available. We are also asking for the slides. So Jordi is going to publish all of that soon on the 5G Mac website.